Good afternoon. In the morning class, we have discussed about Banker's algorithm, which is under deadlock avoidance. I will show you once again. So these two are the avoidance algorithms. Under the avoidance algorithm, we need to discuss about two topics: single instance resource type, and the second one is a multiple instances of a resource type. If you observe here, single instance of resource type means there is only one resource available in each type. For example, there is R1 resource. There is only one resource of type R1 is available in the system. For example, there is another resource R2. There is only one resource of type R2 is available. So then it is called as single instance of resource type. So we can avoid the deadlock by using resource allocation graph, right? How can you avoid? By using a climb edge. This is called as a request edge. Follow the cursor. This is called as a request. This is called as assignment edge. Why? Because R1 is assigned to P1. The arrow mark is directed towards the process, and this is called as a request edge. Why? Because P2 is requesting R1. The arrow mark is directed towards the resource from a process. So this is a request edge, and this is an assignment edge. Okay. What about this dashed line? Initially, these dashed lines are called as climb edges. Climb edge means the process may request the resource at the time. Here there is only one resource of type R2, process P1 or process P2. These are the only two processes in this particular example. So these two processes may request the resource. So that is the reason why may request. So that is the reason why you are having a climb edges. When the climb edge will convert it to the request edge, for example, if a process requests the resource, then it will be converted to the climb edge. Okay, climb edge to request edge. Initially, it is a climb edge dashed line. That means the process may request the resource. Okay, after that, the climb edge will be converted into request edge. That means solid line. Okay, when it will be converted from climb edge to request edge, when the process request for the resource. After that, the request edge will be converted into assignment edge. When it will be converted into assignment edge, when, let me explain with the help of paint. When it will be converted, so initially there is only initially there is P1 process and P2 process. Only two processes were there, P1 and P2. And then there is a resource called as R1, and there is another resource called R2. Initially R1 is assigned to P1, so this is assignment edge, and P2 is requesting R1, so this is a request edge, and this is assignment edge, right? And then coming to R2, initially P1 and P2 may request the resource R2, so these two are called as climb edge. Climb edge means may request. After that, so these particular climb edges will be converted into requested edges. When it will be converted? When the P1 and P2 requesting the process, these line become the solid line. This dashed line will be converted into solid line. So after that, this climb edge will be converted into the request edge. After that, the request edge need to be converted to assignment edge. When it will be converted into assignment edge? So whenever you want to convert it into the assignment edge, you need to check for the cycle. For example, if you assign a resource to P1, so what happened? There will be a no cycle. If you assign R2 to P1, what happened? P1 to R1. Sorry. From this diagram, R1 is allocated to P1. R2 is also allocated to P1. And next P1 is requesting R1 and R2. So there is no cycle now. This is not the cycle. So no cycle. No cycle. So we can assign R2 to P1. Okay. But whenever P1 is requesting R2, you should not assign R2 to the P2. If we assign R2 to P2, what will happen? There will be a cycle. Observe here. Okay, this is a cycle, right? Arrow marks. Based upon the arrow marks, there is a cycle. So if there is a cycle, automatically, sorry. If there is a cycle, automatically what happened? There will be a chance of deadlock. So whenever you are converting the request edge to assignment edge, you need to check. If you convert that request edge to assignment edge, it leads to the cycle or not. If there is no cycle, we can assign the resource to the process. We can convert the request edge to assignment edge. If there is a cycle, you should not convert the request edge to assignment edge. Okay, that is it. That is based upon that we can avoid the deadlock. That is single instance. Single instance of resource type. Using resource allocation graph, we can avoid the deadlock. And the next one is the Banker's algorithm. In the morning, I have explained you about the data structure as well as algorithm, safety algorithm. And then we have done one problem. So now I will try to solve the second problem for you. Okay, the same example. This is the example. The same procedure we need to follow. Okay, let me note down the example for you. How many number of processes are there? There are total 4 number of processes. P1, P2, P3 and then P4. Okay, how many number of resources are there? There are 3 types of resources. A, B, C. These are the resources. Okay, A, B, C. And then what about the process? P0, P1, P2, P3 and P4. These are the process available in the system, right? And then how many number of reach resource are available? A10, B5 and then C7. So these are the instances. 10 instances of type A are available. 5 instances of type resource B are available. 7 instances of type C are available. Okay. And then what about this allocation need and available? So this one you will get from the examination paper directly. You no need to worry. The first one is allocation and the second one is the need. Allocation and the second one is the need and the third one is the available. So this all these things you will get from the question paper itself. Directly you can copy and paste. Two three zero and then this one 03320 03320 10010 10010 and then 02212 02212 and then what about the new 743 020 600 and then 011 011 011 and then 431. So this is the problem given to you, right? So what is the sequence? 1 P1, P3, P4, P0, P2. P1, P3, P4, P0, P2. Whether this sequence is safe or not. Safe or unsafe sequence. This is the question. Okay. So what you need to do? So you need to solve the problem. Okay. First we need to give to the P1 process. Okay. P1. So what is the requirement of P1? This is the requirement need. 0 to 0 is the need. Okay. How many given to P1? Something 302 020. So okay, if you observe here in the previous example, what they have given? Max. There is a difference between these two problems. So this is the max. Already we have allocated 0 1 0. How much you require? Need in order to get the need, what you need to do? You need to subtract max from allocation. For example, here in this example, 753, 7A's and 5B type and 3C type are required for P naught maximum. 753. How many you allocated? 0 1 0. So in order to get the need, what you have to do? In order to get the need, what you have to do? 753. In that you need to subtract 0 1 0. Then you will get 7 4 3. This is the need. Okay. Need means, what is a need? Need means max minus allocation. Max minus allocation equal to need. This is the maximum required by A in the previous example, and this is the allocated. This is the maximum need. This is the maximum need 753. But you have allocated 0 1 0. How many still required? 7 minus 0 7, 5 minus 1 4, 3 minus 0 3. How can you tell this one? For example, you requested your friend to give 10,000 rupees. That is your maximum need. But your friend given you 6,000 rupees. Okay, this is allocated. What is the need? How can you say that 10,000 minus 6,000? Okay, what is your need? 4,000. Like that, in order to accomplish the task, A requires, P1 requires 8 type of instances and 5 B type of instances and C type of instances 3. These things required by P naught. How many allocated? We allocated only 0 1 0. Still how many required? So we need to subtract, like 10,000 minus 6,000, we need to subtract these two. This is the maximum required. We allocated 0 1 0. Then what is the need? Need equal to max minus allocation. 7 4 3. Okay, this is the need. In the earlier example, in this example, you need to follow the cursor. Max allocation given. So what you need to do? In order to get the need, you need to subtract max from the allocation. Then you will get the need. Okay, you need to subtract max minus allocation. Then you will get the need. Okay, but in this particular example, they have given directly need. We no need to convert. We need to no need to subtract max minus allocation. Directly they have given a need. Okay. That is the thing. Okay, you need to observe the difference. We no need to calculate max minus allocation like that. Okay. Now let me explain the example. So directly how many number of resources needed by the process? 0 to 0. 0 to 0 is the need for P1 process. In the sequence, the first process is P1. So 0 to 0 we have to give. So how many number of things available? 230 available. That means what you need to do? So from the available resource 230, we need to subtract 0 to 0. So 0, 3 to 3 minus 2, 1, 2. Now 210 available. Okay, you have allocated 0 to 0 to the P1. From the availability, how many number of resources required by P1? 0 to 0. So 0 to 0 is given to P1. So how many are there still available? So you need to subtract 230 with 0 to 0. So these are the resources available still 210. Okay. So after completing the task, earlier how many you are given? Earlier you have given 302 to P1. Now you are allocating 0 to 0. Are you got my point? This is allocation. Earlier already allocated. This one currently still it requires 0 to 0. So you need to allocate this also to the P1. So automatically you are allocating 302 earlier and 020 now. So how many number of resources utilized by the process total? 3, 2, 2. These are the resources required by P1. So earlier you have allocated 302 and now 020. What the value? 2, 2, 3. Total number of resources allocated to P1. Okay. So P1 will complete the task and P1 will, after use the resources, it will release the resource. Whenever you release the resource, those resources are added to these values are added to this value. Why? Because after using the resources, the process has to release the resources. 2, 3, 5. So P1 successfully completes its execution. So P1 completed execution and release all the resources. Now P1 has 0 resources. And then we need to assign to P3. What is the need of P3? 0, 1, 0. Okay. What you need to do? You need to subtract 0, 1, 1 from available resources. Why? Because you want to give it to the P3 process. 5 minus 0 is a 5. 3 minus 1 is 2. 2 minus 1 is 1. Now these are the available resources. Okay. So that means earlier how many resources you have given to P1? P3? 211. 211 you have given earlier. Now 011. How many resources total you have allocated to the P3? 2, 2, and then 2, triple 2. After using these resources, what it will do? After using the resources, what P3 process will do? It will release all these resources. So those will be added to the availability. So 521 already available, and now 222 is added to existing available resources. 3 and then 4 and then 7. So now 743 are available. Okay. P1 completes the task successfully and P3 completes its task successfully. So P1, P3 completes its task successfully. So we need to talk about P4. Next, we need to give it to the P4. So P4 already 002 already allocated. Now it requires 431. Okay. So you need to give 431 to P4. So already available 743. So 4, 3, 1. How many now subtract? You are going to assign 431 from 743. 2, 1, and then 3. So 3, 1, 2 are available now. So what about P4? P4 earlier uses 002. Now you are assigning 431 from 743. So total how many allocated to P4? 3, 3, 4. Okay. So So after using these resources, P4 completes its task. Why? Because all the needed resources are allocated to the P4. So it completes its execution and release the resources. Release all. So those release resources are added to the 312. So what will be the value? 312, 433. So 7, 4, and then 5. 7, 4, 5. Okay, these are the available resources. So P1 completed, P3 completed, P4 completed. In a sequence, the next process is P0. Okay, you need to talk about P0. So how many resources P0 required? 0, 1, 0 already allocated. It requires 7, 4, 3. 7, 4, 3. So 7, 4, 3 need to be deducted from available resources. Why? Because now the available resources are 7, 4, 5. From those 7, 4, 5, you want to give 7, 4, 3 to P0. If you give 7, 4, 3 to P0, what will be the value? 2, 0, 0. These are the available resources. After giving 7, 4, 3 to P0. So earlier you have given 0, 1, 0. Now 7, 4, 3. Earlier 0, 1, 0 allocated, and now 7, 4, 3 are allocated allocated to the process 0. So 3, 5, and then 7. So after completing the process, it will release the resource. Okay, these 753 will be added to the available. What is available? 0, 0, 2. For 0, 0, 2, you need to add 753. 5, 5, 7 is the available resource after completing the P0. Then we need to give it to the P2. Okay, last one, P2. So how many allocated earlier for P2? 302. Now how many you want to need, how many resources needed to the P2 still? 600. So 755, you need to subtract 600. What will be the output? 551. 551 is the available, now available. 155 after allocating 600 to the P2, we need to deduct from 755 available, so that we have 155 available. So those 600 is given to P2. Why? Because the need of P2 is 600. So 6 plus 3, 9, 0, and then 2. After using it, the resources will be allocated to release and it is added to available. 9, 0, 2. Then 7, 5, 10. Okay. So P2 also completes the execution successfully. That means if we are assigning resources to the process in this order, P1, P3, P4, P0, and then P2. If we are allocating resources to the process in this order, then automatically all the processes are able to complete its job with the help of resources. So it is a safe state. So whether you are doing a correct problem in a correct manner or not, how can we check? At the end of the sequence A, B, C, what is the value of A here? 10. What is the value of B here? 5. What is the value of C here? 7. So 10A instances and 5B instances and then 7C instances. That means at the starting we have a 10, 5, 7, and at the end of the result also all the process completes execution, so all the resources are released. So we need to have total resources A10, B5, and C7. So the answer is correct and it is a safe sequence. Why? Because we are able to provide the resources to every process running in a mission. Okay, that is about Banker's algorithm. So you need to check whether they are giving need or max. Okay. In the problem, if they are giving allocation, max, available, what you need to do? You need to, by using allocation and max, what you need to do? Convert this to allocation, need, available. so that it will be easy for you. So max allocation means 100 for example. Max means 732. So what is the need? What is the need? 732 minus 100. So 236 is the need. So we need to convert this by using these two data structures. We can get the need so that you can solve the problem easily. In the first example, they have given only allocation, max, and available. In the second example, they have given allocation, need, and available. Need means you no need to calculate directly in the problem. If we get the need, we no need to subtract max from allocation like that. Directly, we have a need. So if the resources are available, we can assign those number of resources based upon the need of a process. That is the thing. Okay. And the next concept is deadlock detection. So far, we have completed deadlock avoidance by using single instance resource allocation graph, and then we had to talk about bankers algorithm, safety algorithm, and then now we are going to talk about deadlock detection. So how can we detect the deadlock, and how can we recover from the deadlock? After detecting the deadlock, how can we recover from the deadlock? Okay. So what we need to do? Allow the system to enter into the deadlock state. First, we allow the system to enter into the deadlock, and then we need to uh, find the deadlock by using a detection algorithm, and then we need to recover from the deadlock. Okay. So there is a single instance of each resource type. Here we have only one instance for one resource. R1 means there is only one R1. R2 means there is only one R2. There are no multiple instances, only single instance of resource type. Okay, is a single instance of resources available in the system. So we need to talk about wait for graph here. What is wait for graph? We need to think about the theory. So directly we can move to the diagram. Here if you observe how many number of resources are there, resources R1, R2, R3, R4 and R5. By using this particular graph, we need to draw the wait for graph. If the wait for graph consists of cycles, then there is a deadlock. Simple. Have you got my point? So let me draw the same diagram. So based upon the resource allocation graph, we'll construct wait for graph. So in our example, P1, P2, P3, P4, P5. So these are the resources. And then R1, R3, R4. R1, R3, R4. R1, R3, R4. R1, R3, R4. And then R2, R5. R2 and then R5. Then what are the directions? So this is a diagram. So based upon this will be given to you, right? And next, based upon this, you need to draw the wait for graph. So what is a wait for graph? So for example, here we have 5 processes P1, P2, P3, P4, and P4. So what you need to do is P1. P1 is waiting for R1 and R1 is allocated to P2. P1 is waiting for R1 and R1 is waiting for R1 is allocated to P2. So there is a P1 is waiting for P2 indirectly. Are you got my point? P1 is waiting for R1, but R1 is assigned to P2. What you need to do? Directly there is a connection between P1 and P2. That means P1 is waiting for P2 indirectly. So P1 is waiting for P2. Okay. And then coming to other part of P1. Let me complete all the connections with P1. Okay. Here also P4 is requesting R2 and R2 is assigned to P1. Have you got my point? There is only one outgoing connection and incoming connection for P1. Let me complete with P1 first. And then we will move to P2 and then we will move to P3 and then for P4, P5. So that it will be not creating any confusion, right? So P1 is requesting R1. R1 is allocated to P2. Okay. So directly P1 is waiting for P2. So P1 is waiting for P2. Okay. And then P4 is requesting R2 and it is allocated to P1. That means P4 is waiting for P1 indirectly. So P4 is waiting for P1. Why? Because the resource R2 is allocated to P1. So P4 is waiting for R2 and R2 is allocated to P1. So indirectly P4 is waiting for P1. So P1 connections are over. Come to P2. So for P2 we have multiple connections. If you observe here, with P1 and P2 already done. P1, P2 connection already done. We need to talk about the remaining parts, right? P2 is waiting for R3. This is R3. Okay. P2 is waiting for R3, but R3 is assigned to P5. That means indirectly P2 is waiting for P5. Okay. And then P2 is waiting for R4 and R4 is allocated to P3 or assigned to P3. That means P2 is indirectly waiting for P3 also. Okay. And then what about R5? P2 is waiting for R5 and it is allocated to P4. P2 is waiting for R5 and is allocated to P4. That means P2 is also waiting for P4. This is a connection. This is the connection, right? So P2 is also done. And then all the connection, this direction, this one, and this one. Now you need to talk about P3. Okay. So P3, this connection is already done. P2 is waiting for P3. P2 is waiting for P3. P2 is waiting for P3. So that is done already. Now P3 outgoing connection. So P3 is requesting R5 and it is allocated to P4. So P3 is requesting for R5 and it is allocated to P4. So it is waiting for P4. So P3 is also done. And next, what about P4? So for P4, we have two connections, this direction, this direction. So P4 is requesting R2 and it is allocated to P1. So P4 to P1. So P4 to P1 already done. And then R5 is allocated to P4 and P3 is waiting for R5. So this direction. So P3 to P4 is also done. Now we need to talk about P5. Only one incoming connection. So P2 to P5. So P2 to P5 done. So we're done with P1, P2, P3, P4 and P5. So this is called as wait for graph. So if there is a cycle, then we can say that there is a deadlock detected. Okay, it is called as single instance wait for graph. Single instance. Why? Because there is only one R1, one R2, one R3, and one R5. There is only one instance of references available in this example. There is only one resource R1, one resource R3, one resource of type R4, one resource of type R5, one resource of type R2. So this is called a single instance resource allocation graph. Okay. So based on this single instance resource allocation graph, this is called as resource allocation graph. How the resources are allocated to the process. That is the reason why it is called as resource allocation graph. So by using this resource allocation graph, you need to draw wait for graph. If there is a cycle, then there is a deadlock. Observe here. There is a cycle. There is a cycle. Right? And again there is a cycle. Here also. Right? So likewise, we have a cycle. This is not the cycle. This portion. Only this one, this one, this one, and this one. This is a cycle. Outer two. Okay. So if there is a cycle, then there is a deadlock. Why? Because arrow mark to this, and this will be connected to this, and it will be connected to this, and it will be connected this. Again, this will be connected this, like there is a cycle. Okay. So if there is a cycle in the wait for graph, there is a deadlock. Okay. That is called as wait for graph. And then, so here also we need to discuss about one algorithm, the same as usual. So there are three types of data structures here: available, allocation, request. Available means available number of resources of each type. Several instances. When there are several instances means each resource having different number of instances. That means R1 is of 5 instances available. Resource R2 some K instances available, like that. More number of instances of resource. If there is only one instance, we need to go for a resource allocation graph. From that, we need to draw the wait for graph. If it is a single instance, if there are multiple several instances, we need to go for algorithm. So what is that one? Follow the cursor. Available, allocation, request. Available means available number of resources of each type. Allocation means how many resources allocated to the process. Request, maximum number of resources requested by the process. Max means, for example, you require 8 resources, but allocated is 6. Have you got my point? Maximum resources required by the process is 8, for example, but you allocate only 6 resources. How many is still required by the process? 8 minus 6 equal to 2. It requires 2 resources. Available means total number of available resources in a mission. For example, 10 resources available, maximum resources required for the process is 8, and then you allocated is 6. Then what is the need? Need means allocation minus request minus allocation. Request means max. Max 8 requested, allocated 6. 8 minus 6 is 4. Okay, what is available? It requested 8, but you allocated 6 now. So total number of available are 10. 10 minus 6 are 4, like that. Okay. The same, it is called as a detection algorithm. It is almost similar to the safety algorithm. So initially, work equal to available. I already told you for I equal to 1 to swan n. So that means there are n number of process, and initially all the process are not completed its task. So initially finish of I equal to false for all I. For example, if finish of I equal to true means all the process already completes the execution. No need to run the algorithm. If the finish of I equal to false, then what we need to do? Our request must be less than equal to work. What is work? Work is available. Available means available number of resources. Available number of resources are 10, but you are requesting 12. You should not request the resources more than available in a machine. Okay. Are you got my point? So work means available. Work equal to available. You can substitute here. So you request, the process request need to be less than available. Okay. If not, and the finish of I equal to true and request is not less than work, automatically you need to go to the fourth step. That means the system is in a deadlock state. That means the process requires more number of resources available in a machine. So we cannot give the resources. Why? Because only system we have 10 resources available, but it is requesting 12 resources. How can we assign? We cannot give, right? So automatically system will be moved to the deadlock state. Why? Because we cannot provide the resources. For example, if a process requesting the resources which are less than available, then automatically what we need to do? We need to go to the step 3. So we will allocate the resources to the process. Initially work means available, and work plus allocation. Work equal to work plus allocation means, I will let you know what is work equal to work plus allocation. So actually earlier, for example, there is a process called P3. Already you have given 0, 2, 3 resources to P3. A, B, C. And then what it needs? It needs still 4, 5, 4, 5, 3. Okay. And then available. So available means how many number of resources still available in the machine. So there are 6, 7, 4. These are the number of resources available. So what you need to do? Already you have assigned 0 to 3. And then now it requires 4, 5, 3. So what you will do? From 764, 674, you need to deduct 453. So 2, 2, 1, 2, 2, 1 are still available. After giving 453 to process 3, still how many available? 2, 2, 1 available. Okay. So now you have allocated 453. Earlier you have allocated 0, 2, 3. So total how many resources allocated to P1? So 453, 0, 2, 3. What are those? 3 plus 3, 6. 5 plus 2, 7. 4 plus 0, 4. So total 476 resources are allocated to P3. Earlier 0, 2, 3 allocated. Now 453. Total 476 are allocated to P3. After use, what it will do? It will release all the resources. So these resources will be free after use. So those resources will be added to available. After completing the task, what you will do? You need to add those to available. So 7, 9, 6 are available. So after completing the task, you need to add them to the available. So here work is available. What you are adding? So available plus work. Sorry. Allocation. Allocation plus work. Allocation plus work means allocation plus work means this is the allocation 0, 2, 3, and this is also allocated 4, 5, 3. Now the allocation is 4, 7, 6. Available is 2, 2, 1. Work equal to available. I already told you work equal to available here in our example. So the availability is 2, 2, 2, 1. What is allocated? 4, 7, 1. 4, 7, 6. These 4, 7, 6 is added to available. So work equal to work plus allocation. Allocation means earlier we have allocated 0, 2, 3. Now we allocated 4, 5, 3. So total 4, 7, 6 allocated. What is available? 2, 2, 1. So if we add 2, 2, 1 plus 4, 5, 4, 7, 6, 6, 9, 7. So what is available now? Work equal to 6, 9, 7. Work means available. Work equal to available. Go to the previous slide. Observe here A. Work equal to available. So here 697 now available. How can we get the 697? How we are getting 697? By using a formula called work equal to work plus allocation. What is work plus allocation? So work is available. Earlier, how many available? 2 to 1 available. Okay, how many allocated to the process? 476. By adding those two, we will get 697. Okay. Now in a system, 697 resources are available. So work equal to 697. That means available equal to 697. So it is completing its task. That is the reason why it is releasing the resources. When it completes the task, automatically, what will be the status of finish? Finish equal to true. That is the reason why it releases all the resources. So finish equal to true. Like that, we need to complete for every I equal to 1, I equal to 2, I equal to 3. Like that, you need to assign resources to the process. So whenever there is a problem, the request is more than the available, then automatically the system will be moved to the deadlock state. If a process requires more number of resources than available, automatically you cannot assign the resources to the process. So you cannot complete the execution of a process. That means the system is in a deadlock state. If a process is not requesting the resource more than available, automatically you can allocate the resources to the process, and it will complete the using the resources, and it will release the resources, and those resources are added to the availability, and it will be used by the other process. Like that, the sequence will be continued. Okay. If you are unable to give a resource to the process, means automatically we are in a deadlock state. That means finish of I equal to false for any I, and for any process. It may be first process to end process. For any process, we are unable to give the resources, then the system will be in a deadlock state. That means for that particular process, finish of I equal to false. That means the process is deadlocked. Okay. The same problem. Here allocation on the request available. Request means max. So P0, P2, P3, P1, P4. For all the process, if finish of I equal to true. That means you are able to complete the process in this particular sequence, P0, P2, P3, P1, P4. If we allocate the resources to the process in this sequence, first we need to give the resource P0, and then you are able to give the resource to P2, and then you need to give the resource to P3, and then you need to give the resource to P1. At last, you need to give the resource to P4. If we are able to complete the process in this particular sequence, for all these process, finish of I equal to true, and finish of 1 equal to 2, finish of 2 equal to, finish of 3, finish of 4, finish of 0 for P0. For every process, finish of I need to be true for all I. So then the system is in the not in the deadlock state. If you are unable to give the resource to the process in the sequence, then automatically the system is in a deadlock state. Okay. You need to solve this particular problem on your own. I have given already 2 examples to you. It is up to you to solve the problem. And next, last topic, recovery from the deadlock. So what is recovery from the deadlock? So already I have shown you one wait for graph, right? Here, follow the cursor. So what is the reason for the deadlock? Cycle, right? So in order to, if you detect a deadlock, in order to recover from the deadlock, what you need to do? You need to abort from one process from the cycle. If we abort one process from the cycle, automatically there will be a no cycle. If there is no cycle, automatically no deadlock. Which process you need to remove from the cycle? Which process you need to abort in order to remove the cycle in the graph? That is called as recovery from the deadlock. Abort all the deadlock process. That is the first technique. You can abort all the deadlock process. Then within the cycle, how many number of processes are involved, you need to remove all the process. That is one technique. And the second technique, abort one process at a time until the deadlock cycle is eliminated. That means you should not eliminate all the process involved in the deadlock cycle. Okay, you need to abort one process at a time and again check for the cycle. Again one abort one more process, check for the cycle. Like that, you need to abort the process one by one. If you abort all the process, now what is the problem? You need to run all the process again from the starting. So it is a foolish idea. In order to avoid such a problem, so what you will do? You will abort one process and check for the cycle. If there is still a cycle, then again you need to abort one more process. You need to remove one more process from the cycle. Okay. Again you need to check for the cycle. Like that, you need to remove one process and check for the cycle. So this is the second one. And next, okay, you want to remove only one process at a time. Then which process you need to select as a victim process? If you observe in this diagram, sorry, here. So in this particular diagram, P1, P2, P3, P4, and then P1. P1, P2, P3, P4, and then P1. This is a cycle, right? So four processes are involved in the deadlock. Which one you want to? Which one you want to select as a victim process, right? So these are the conditions. These are the criteria. Sorry, these are the things you need to consider when you want to remove one process from the cycle. What are those? You need to check the priority of the process first, whether the process is high priority process or low priority process. And then how long the process has completed. That means how much time from how long it is being executed by the CPU. Okay. And next, how many resources a process has used. How many resources a process need to complete. For example, how many used already, how many resources needed by the process to complete the execution. How many process will need to be terminated. How many number of process, such a process you need to terminate in order to recover from the deadlock. Is a process is interactive process or a batch process. So you need to consider all these situations whenever you want to remove a process from the deadlock cycle. Okay, you need to check for the priority, and then always you need to choose the low priority process, right? High priority process should not terminate. And then how long a process is completed. For example, a process requires 10 milliseconds of CPU time. So it executed from last 8 milliseconds. Just 2 more milliseconds required to complete the task. You should not choose such a process as a victim. Okay, if you choose such a process, what happened? Again, you need to run the process from the starting later time. Okay, that is the problem. And next, the process requires total 5 resources. 4 resources already utilized by the process. Only one resource it required. Okay, if we abort such a process, what happened? Again, you need to start the process from the initial point. Again, you need to assign all the 5 resources to the process later time. So you should not remove such a process. You should not choose such a process, right? So whenever you want to choose the a process, you need to consider the priority as well as how much computation time already, how long the process is being executed, what are the resources already utilized by the process, what are the resources still needed to complete this task, whether it is interactive or a batch process, single process or a batch process, and how many number of such a process you want to remove from the system in order to avoid the deadlock. So here there are some problems with the recovery from deadlock. So what are those? Selecting a victim. Whenever you are selecting a victim, one process, in our example, P1, P2, P3, and then P4. So in those 4 processes, which one you want to select as a victim? So whenever you select a victim process, the cost need to be low. I already told you, it is not a high priority process. It should not use much system resources at, and next to it should not, and it should not utilizing the CPU time much. So such a process you need to select. So the cost of selecting a victim must be low. And then roll back. Roll back means return to some safe state. Restart the process for the further state. That means you need to uh, remove some of the process, and where you stop the from that moment onwards you need to restart the process. That is called as rollback. And then starvation. So whenever you pick a particular process as a victim process, so each time you should not pick the same process. For example, I already told you in a mission we have a high priority process as well as low priority process. Every time if you choose a low priority process as a victim process, then the low priority process will never get a chance to complete its task. So for that purpose, what you need to do, the low priority process should not always choose as a victim. For that purpose, what we can do, that problem is called as starvation. Always the low priority process will be selected as a victim process. Okay, that is a starvation problem. So how can we avoid that problem? I already told you earlier when we talk about CPU scheduling algorithms. Aging. Aging means if the process is having a low priority, for time being you can select it as a victim and you can remove from the deadlock cycle. But again the process will be entered into the machine. Again it will be under execution. Again, it may be in the cycle. So you should not select the same process again and again. For that purpose, you need to increase the priority of that particular process based upon the aging. So how old the process is. If the process becomes old, getting older, automatically the priority of the process will be increased. So that at one time, the low priority process will become a high priority process. Okay, then it will have a chance to complete the task. Okay, that is about recovery from the deadlock. So this is the end of the session. So if you have any doubts, let me know. So with that, we completed what is deadlock, necessary condition for the deadlock prevention, what is the system model, request, use and release, what is resource allocation graph. So how can we find whether the deadlock is occurred or not with the help of resource allocation graph. If it is a cycle, then it will be a deadlock. In some situation, even if there is a cycle, we cannot consider it as a deadlock if there are multiple instances of resource available. Okay, and then deadlock avoidance. In the deadlock avoidance, we have two things: single instance, that means climate, that example, and then we need to talk about Banker's algorithm, safety algorithm, and then after that we have discussed deadlock detection. Under that we have discussed wait for graph. Later we had a discussion about deadlock detection using algorithm. After that, recovery from the deadlock. Okay, so this is about deadlocks. We have completed this. By this, we have completed 3.5 units successfully. Okay. So you have any doubts? Do you have any doubts? Do you have any doubts? Let me know. Otherwise, at least you need to respond to my query. So whether you have doubts or not, I can end the session. 24 participants are there. Still, I am talking to you people, but you are not responding properly. Why? No doubts. Okay. Thank you.